Hey, our big picture today is solving differential equations. Now, that name terrifies people right off the bat. Differential equations. I want to remind you, the first day you ever did antiderivatives, okay? The first day we did antiderivatives, if you were in my class, I do this example. F prime of x equals 2x. What is f of x? Anybody? What is f of x? I'm telling you the derivative of a function is 2x. F of x is
X squared.
x squared. Now, somebody might say, well, how about x squared plus 5? And someone else might say, well, what about x squared minus 3? Are you both right?
Yeah.
Yeah. Oh, x squared plus any number, its derivative would look like this. So we say, let's throw in an arbitrary constant because the derivative of this is this. So if I drew a graph of my solutions, and this is part of today's lecture, by the way, also, I get what is affectionately known as the candelabra of parabolas. Try saying that fast 3 times. I think that's going to be the new drunk test. The candelabra of parabolas. Here are parabolas that are only differing by a constant. And every one of these have the same derivative. This is what is called a family of curves. Okay? A family of curves means they all have the same derivative, but they differ by a constant. So how do I know which one this is? Oh, okay. What if I also told you f of 1 is 3? Let's suppose I told you that information as well. Well, if f of 1 is 3, then what would that make my c?
2.
2. So the specific curve, the only one of these curves that passes through the point 1, 3 would be this one. Okay, so that's called a specific solution. This is the general. Oh, sorry, let's see. Sorry, plus 2. The only way I can get a particular solution is to have what's called an initial condition. Now, sometimes you're given initial conditions, sometimes you're not. But the whole point of this is day 1 of antiderivatives. When I first introduce an antiderivative, the very first thing I do is this. This is a differential equation. So you started doing differential equations the day you started integrating. A differential equation is any equation that involves a derivative. That's it. And the only way you can solve a differential equation is by integration. So that's kind of the theme for today. So this is old stuff. This is not new information. This is how we started the process. So with this, now I want to remind you of stuff that you already know, but maybe a little bit rusty. And that is the concept of integration by substitution. So let's remind ourselves. If I said y equals f of g of x, it's called a composition of functions. Most of the functions we deal with are compositions, right? We don't just have sine x, we have sine of a function of x. We don't just have e to the x, we have e to the function of x. I don't just have x raised to a power, I have function raised to a power. So most of the time when we're dealing with functions, we're dealing with compositions. So if I want the derivative of this, it's f prime of g of x times g prime of x. This is called the chain rule. And we're very aware of that. You cannot take a derivative in general without the chain rule. So whatever my inner function is here, this is the derivative. So if I asked you, I want to differentiate, let's say, e to the tan x, okay? Well, the answer is e to the tan x times the derivative of tan x. So my final answer would be e to the tan x times secant squared of x. We're very familiar with that. So then if I wanted to integrate that quantity right there, then I would get back my original function. Okay, no big deal. So we want to talk in general, how do you integrate that to go backwards? So we will make no assumptions. We want to go through the process again. So I know the following is true. I know that if I integrate f prime of x dx, I know I'm going to get f of x plus constant. I know that's true. But what if I want to integrate f prime of g of x dx? Can I integrate this and get an answer? The answer is no. I need the whole statement to be able to integrate, because we already know the derivative of this is the entire thing. So I cannot do this problem. What I can do is this problem. And I know what the answer to this question is. F prime of g of x times g prime of x, the antiderivative is this, because that's where it came from. So let's walk through the process to get there. So generally what we do when we see a composition of functions, we see stuff, we recognize this guy here because we call that the chain rule factor. So what we do is we say, let's let u equal g of x. So it's implied that u is a function of x. Okay, there's no question. Then if I differentiate with respect to x, we say du dx is g prime of x. Okay. Now, x is the only independent variable in the problem, which means when I integrate, I have to integrate with respect to x. It actually matters what variable you put there. The lack of that thing there creates ambiguity. I actually have to have the instruction. Just like when I said I want to differentiate, I wrote d dx. I have to give a variable there because that's the instruction. So what if I integrate both sides here with respect to x? Then I'd have du dx, which is a function, integrated with respect to x, equals g prime of x, integrated with respect to x. Okay? Here's where substitution gets a little bit wonky for people. Forget the plus c for a moment. Just think about the functions. Isn't the right side g of x? I'm integrating g prime of x. Okay. What's the left side? That's the integral of what? Well, doesn't the left side have to be u? But how do I integrate and get du? The only way to, or get u, the only way to do that is that I'm integrating 1 du. Now, this is almost a chicken egg thing. Which came first? The integral of du dx with respect to x is exactly the same as the integral of du. How do I know that? Because the integral of du is just u. And the integral of g prime of x is just g of x, which is my original substitution. So I know this is true. And here's the way it works. This is a function. The derivative of u with respect to x is a function, but I'm only going to see u's. I'm not going to see any x's in that statement. I'm going to see u's. So when I integrate this with respect to x, it's the same as if I integrate du. dx's do not cancel. They are not quantities. dx is an instruction. But the result of this integration is identical to the result of this integration. Okay? So if I go backwards, here's where the substitution comes in. Now let me go backwards. The left side is now the integral of du, and the right side was g prime of x dx. Du and dx are not quantities. They are instructions. They're telling me what I'm integrating with respect to. So the integration of g prime with respect to x is equivalent to just integrating with respect to u. So this step here, when we're doing a substitution, most of you are very familiar with this step. You said let u be g of x, and at this point in the game, what we usually do is we write and du is g prime of x dx. This is what we do in Calc 1. And you're saying, but you said du and dx are not quantities. No, they're not. They're instructions. Because I'm saying this integration is equal to this integration. Boom. But when I'm doing my substitution within the integral, there's already an integral symbol left. So I replace this instruction with this instruction when I change the variable. So let's physically do that, okay? So I'm gonna go back to the start. I know I don't have a lot of room here. The process isn't complicated, but it's the why sometimes it's important. So I have the problem f prime of g of x times g prime of x integrated with respect to x. And we said let u equal g of x, then the du is g prime of x dx. Du dx integrated with respect to x is the equivalent of g prime of x integrated with respect to x. So I am going to replace this instruction with this instruction when I replace this variable. So this is now the integral of f prime of u, and this is du. That's how substitution works. I'm replacing an instruction with a different instruction. There's very few absolutes in math, and one of the absolutes is when you change a variable, you change it all at once. There is no statement that has an x and a u in the statement at the same time. I am replacing g of x with u, which means I'm replacing this instruction with du. There's no mathematical statement that has x's and u's. That's an absolute impossible statement. In Calc 3, you're going to learn how to integrate with more than one variable at the same time in the integral. In Calc 1 and 2, we can only have one independent variable. So you can never have an integral with the independent and the dependent variable at the same time. There is no problem that has two variables in the same integral at the same time, because there's only one independent variable. That's what I'm doing, is I'm replacing one with another. So if I continue this, the integral of f prime of u du is just f of u. And now we'll go and substitute back. Now, we already knew that was going to be the answer, but this is the route we took to get there. Now, if it's a definite integral, then I evaluate the definite integral. I'm not worried about that. In fact, in Calc 2, we don't spend a lot of time on definite integrals because we spend a lot of time on how to do the integrations. We're going to learn a whole bunch of new techniques of integration. Definite integrals are necessary, but that's just one more step. That's just evaluating my answer. That's not really the calculus of things. Okay, so this is a quick review. I've got a whole worksheet with lots of examples on it. Now I want to see how this applies to a differential equation. So we're going to start with the most basic common differential equation that is, and that's the population growth differential equation. The most common differential equation. Let's say that y of t is the population at time t. Now, if it helps you think of y as people, y could be fish in the sea, y could be bacteria in the petri dish. It's whatever I'm counting. So if it helps you to think of people, that's fine. Population of people. So if y of t is the population at time t, the most common differential equation that describes population growth is as follows. dy dt, that's a terrible d. dy dt equals k times y, where k is a constant. This is the most common differential equation that exists. This is the one that describes population growth. So think of it this way. Think about money in the bank, right? You're going to deposit some money in the bank, maybe a large sum of money, maybe only a little bit of money. You don't say, I'm going to deposit money in the bank and the interest I get every month will be $100. No matter how much I deposit, I'm going to get $100 interest. I don't think it works that way. I think the more you deposit, the more interest you get. And in fact, don't you get interest based on how much you deposit? So isn't the interest you get somehow a multiple of how much you deposited? Oh, so my rate of growth of money is going to be a constant multiple of how much I deposit. Well, populations go the same way. You don't say, in San Diego County over the last 10 years, the population has grown this many people per year. No, you say the population has grown by this percent per year, because a population is always going to grow as a percentage of what is already there. Okay, so hang on one second. I've got to find my mouse here. Okay, that was the spam call, but it would ring 5 times and the loud message was going to come on. I'm like, no, I don't want to do that. So the population grows at a constant rate. Now, by the way, this could also be the population decays at a constant rate. If k is a positive number, it means I have population growth. If k is a negative number, it means I have population decay. right? I'm losing people. So in other words, I have something that's decaying at a constant rate. Now, I would like to solve this and get something. So when I'm looking at this, I'm saying, how am I supposed to solve this? Well, y is the dependent variable, t is the independent variable, and I'm going to have to integrate. And by the way, what variable am I going to integrate with respect to ultimately? Is t. So what we're going to do is we're going to get the y on the left side first. I'm going to write it as 1 over y dy dt, and that equals constant. Now we're going to integrate both sides with respect to t. So the left side is 1 over y dy dt. dy dt is a function. dy dt is not an instruction. It would actually be the derivative of some function, and I'm integrating that with respect to t. But there are only y's in that statement. The right side is k with respect to t. Now, we just did that problem with substitution a moment ago, and I said, when you integrate dy dt with respect to t, that's exactly the same as integrating with respect to y. dy dt integrated with respect to t is integrating with respect to y.
Professor,
Yes.
sorry to interrupt, but the glare in the center, what does it say again right there?
Thank you.
I can't see what it says.
Yeah, unfortunately, when I'm moving in and out, the glare changes for me. On the right side, it's the right side, it's k dt. There we go. I just integrated both sides with respect to t, so that's the right side.
Thank you.
Now, my left side is 1 over y dy. My right side is k dt. Well, that one's easy. K is a constant. So what's the right side going to be? The right side is going to be just kt plus constant. Agreed? What's the integral of 1 over y dy? We know that one. What will that be?
ln.
Good. Natural log. So the left side, hopefully you can see this, is natural log absolute value of y. The right side is, oops, I put k dt, sorry. The right side is kt, and I'm going to call it c1 because we're going to have more than one constant at some point. So the left side is this, the right side is this. My goal is to write y equals. Okay, now y represents population. Can population be negative? No. So is the absolute value necessary at this point? No. So we're going to exponentiate both sides. That's how you get something out of a logarithm. So I'm going to go e to both sides. So now the left side is y, the right side is e to the kt plus c1. Well, according to rules of exponents, right? I know this one, x to the a times x to the b, isn't that x to the a plus b? I mean, it's not the rule of exponents. When you multiply with the same base, you add exponents. Hopefully that's the rule you guys follow. So with that, can I pull this apart? Yeah, how about e to the kt times e to the c1? Okay, c1 represents an arbitrary constant. So tell me about e to the c1. If c1 can be any real number, tell me about e to the c1. Is that a specific value or is that also any number?
Still a constant.
It's still a constant. Now tell me, if c1 can be any real number, positive or negative, because it can e to the c1 be any real number? E raised to the c1, can it be any real number? No. It can be any
Positive number.
Any positive number.
because it's e can't be negative. E to the c1 represents any positive real number. So why don't we just call that, I don't know, c2. All right. Wow, look what I've got so far. I've got y equals constant e to the kt. This k shows up as an exponent. So we're almost done. We have one more step. I mean, I'm going to go ahead and erase this so I can fit it in the middle here. So now I've got y of t, let me write it like this. Y of t equals constant e to the kt, where c2 could be any real number, or could it? I didn't give you any initial conditions. when you're doing any type of population growth or decay, you have to have a starting amount. So if I said, for example, in San Diego County, there are 1.5 million people, at midnight, January 1st. Okay, I got to give you a day or a time. I got to give you some starting point, and that 1.5 million people would represent my starting amount. So now I can ask a question like, if the population grows at this rate, what will the population be in 1 year or 5 years or 10 years? Whatever. But I have to have a starting amount. I have bacteria in the petri dish. I have, 10 million bacteria in there when I start. You have to have a starting amount. That's always the y of 0. So what if I do this? Erase this. Y of 0, which we often write this way. Most of you are familiar with this from science classes. Whenever you have a subscript of 0, that always means starting amount. So y of 0, that's how many people I have at the start, is equal to what? C2e to the 0. I'm replacing t with 0. But wait a minute. E to the 0 is just 1, isn't it? So C2e to the 0 is just C2. So that arbitrary constant in front of the E is not arbitrary at all. It's actually the starting population. Oh, not arbitrary, not any real number. It's very specifically the starting population. We have just solved this differential equation. The solution of this differential equation is y of t equals y0 e to the ket. This is often considered the most important of all the differential equations because it's the one that's probably the most commonly used. We actually use this to help design infrastructure of cities. Now, when you were kids, you remember, like in your history classes, things like, in 1976, the world's population was 4 billion. You remember things like that. Doesn't that make it sound like from January 1st to December 31st, the world's population was 4 billion. It changed none. Then at midnight, December 31st, it now was some other amount. Well, no, populations don't do that. Populations continuously change. It would be safer to say at some point in 1976, the Earth's population hit 4 billion, and it was probably there for a few seconds, and then it went past it. We often say things like that, but it doesn't make a lot of sense, right? The population in San Diego, whatever it was when class started, it's probably a little bit bigger now because people have been born. Probably more people have been born than people have died in the last half an hour, okay? So populations change continuously. What I can say is if the population has grown at a certain rate in the previous history, then if it continues to grow at the same rate, we can predict the population in the future. That's always safe to do it that way. But to say what will the population be next year, you don't know. That'd be kind of like saying, what is the score of the Super Bowl going to be? You can say the most likely is this. So let's take a really simple population situation. Okay, let's do it. Let's say in a particular town, let's say the population, I like to do it this way. The population, January 1st, 2000, right? Well, right when we hit January 1st, 2000, the population was, let's say, 187,630 in a particular town, okay? If the growth rate for the next 25 years is, how about 2.47%, find the population January 1st, 2025. Now, that's a big if. We're saying if the population growth rate basically remains constant, which that's not always going to happen, but I can say if it is constant, can we predict the population in the future? Yes, that's exactly what we do in any town. We say based on recent history, we will project. The reason we do that, let's say there are parts of San Diego that are growing much more rapidly than other parts. Well, if we don't address that, then we have housing shortages, We have a shortage in schools, a shortage of police, a shortage of fire. We have a shortage of all of these basic services if we don't address the fact that we believe the population will grow to a certain amount. So that's what we do. We're proactive, right? We might need additional lanes on the freeway if we believe a certain area is growing particularly fast. So we want to do the mathematics of this. So all we have to do, okay, what is this number? That number is y sub 0. What are we asking for? Y of 25. Okay, in this problem, y of t is 187,630 e to the what? This is my k, that's my growth rate. 0.0247. Yeah, don't say 2.47. That would mean we're growing over 200% per year. Now, I want y of 25.
Maybe if we're doing like bacteria, we could do that.
Bacteria might grow that fast. There you go. So, and by the way, do the entire problem using a calculator. So let me grab a calculator. Okay, so I'm going to do this whole thing on my calculator. So I'm going to go e raised to the 0.0247 times 25. And all of that's times 187,630. So hopefully all of us get the same answer. Okay, now this is population. This is going to be an infinite non-repeating decimal sequence. So I need to round it off at some point. So I'm going to give you a decimal roundup. That's what equals with a dot is. Squiggle means something completely unrelated. Squiggle means asymptotic. If you used one of these, that's probably not the symbol you're using. So I've got 347,919.7809. Keeps going. Now, is this a good final answer? What do you think?
You can't have a fraction of a person.
Good, good. If this represented a quantity, a measurement, this represented an amount of water, or if this represented a time, or if this represented mass or weight, could I have decimal values? Yeah. If it's a continuous measurement, any form of measurement is continuous. Height, time, weight, speed. Anytime you're doing a measurement, you technically have an infinite number of decimal places. We're counting people. This is what's called a discrete measurement. And in calculus, most of the time we do continuous measurements. But when you're doing a discrete measurement, okay, you hit it right on the head. You can't have decimal people. That doesn't even make sense. So in a discrete measurement, maybe I'm measuring the number of cars, that came off the production line. Can you have 0.78 people? No. So how many people do you have? The question is, what do you do with this decimal? By the way, what I'm going to tell you is an absolute, always true, unchanging. It doesn't matter what the scenario is. It's always the same thing when you're doing a discrete count. What do you do with the decimal? Do you go up?
Truncate?
You truncate. Good. What does truncate mean, literally?
Just cut it off.
Lop it off. People think cars. I think cars is the easiest example. What does the 0.78 mean? It means we're more than halfway through producing that car. Are we going to sell the 0.78 car? No, that car doesn't exist yet. It's not a whole car yet. So we have this many cars. We have this many people. So when it comes to discrete counts, it doesn't matter if it's 0.99, you haven't got there yet. You don't get to round. And I explained it this way to somebody. You fell into the well. The well is 30 feet deep and you scratch and clawed your way. 30 feet, you got 29 feet, 9.5 inches. And then you slip back down and you never made it out. You know what? You were almost to the top, but you didn't get to round up and be at the top because you never actually made it to the top of the well. You see, there's no rounding up when you're trying to climb out of the well. There's no rounding up when you're trying to, how many completed things. Now that I know that sounds silly, but this is always true. In a discrete count, you truncate. In a continuous count, you round. And you round to whatever an appropriate number of decimal places to report is. So in a measurement, if you're talking about your weight, you probably rounded to the nearest pound. But if you're talking about your height, maybe you round it to the nearest centimeter or the nearest inch or even the nearest millimeter, whatever's appropriate. If it were time, maybe you round it to the nearest second. Maybe you round it to the nearest hundredth of a second, like in the Olympics. You know, it's whatever's appropriate for the situation. So this is sort of the simplest, lowest level of all of the differential equations, the population growth. Now, this can be applied in many, many other areas. So I want to go now to a more complicated problem, one of my personal favorites. This is one of the first applications I do in a Math 255 course as well. All right, so now you have to understand the scenario here. So we're going to make a simple assumption. We are going to assume that we are in a constant temperature environment. Okay, we're not outside where the temperature might be changing a whole bunch over the course of the day. We're inside a house, we're inside a room, whatever, and the temperature is essentially constant. It's really not changing. Okay, now here's how it works. You're going to take your hot cup of coffee. This is my water bottle. Pretend this is a hot cup of coffee, and I'm going to place it down on the counter in the room temperature environment. What happens to that cup of coffee immediately? Anybody? The hot cup of coffee. What happens immediately? It starts what?
Cooling down.
Starts cooling down. Now, how fast it cools down depends on a lot of factors. You know, what's the temperature? You know, how insulated is the mug? But we all agree it starts cooling down. So let me draw you a picture of this. All right, this is time. This is temp. Oops, temp. Okay, I can't. Yeah, try that one more time. I know, little t, big T usually. So a lot of times we use a little t for this one, we use a big T for this one. Now, this is how hot, this is time zero. The cup of coffee is really hot. Maybe it's 130 degrees, 140 degrees. It's really hot. And we agree it starts cooling down, right? So it starts cooling down, and this, that's the room temperature. That's called A. A stands for ambient. The ambient temperature means the constant room temperature. And it's very important that the room temperature is constant. If the room temperature varies, then the cup of coffee, I can't predict. So the question is, I would like to know if the cup of coffee is a certain temperature, the room's a certain temperature, and I know how hot it is maybe in some future. Can I predict how hot it's going to be in an hour? Can I predict when will it be at a certain temperature? Yeah, there's a whole bunch of things I can do. But first we have to discuss what's happening. So when the temperature starts cooling, it'll eventually reach room temperature, correct? Everybody, it'll eventually reach room temperature? What do you think?
I think that's what my T is at right now.
Okay, so it eventually reaches room temperature. And then of course it goes below room temperature. And it keeps going. Eventually freezing, but it keeps going, eventually approaching absolute zero, which means that all molecular movement stops in a radius that's expanding, and eventually the entire planet Earth becomes a frozen ball of ice and all life dies on planet Earth because you left that coffee out. Or not. See, the question was, I said, when will it reach room temperature? You know what the answer is? Never. That's an absolute impossibility. Because if it reaches room temperature, then that means it's going to keep going. It can't reach room temperature. What? What are you talking about? It doesn't reach room temperature. It's asymptotic to room temperature. The room temperature is an asymptote. What I can get is really, really, really close to room temperature. I can get within, a tenth or a hundredth or a thousandth of a degree of the room temperature, which for all practical purposes would mean, I've essentially reached room temperature. I suppose when I'm within a tenth of a degree of room temperature, I'm not going to, worry about the tenths. This is what happens. It cannot cross that dotted line, because if it does, that means it's going to keep going and reach absolute zero. And again, all life ends. And that's a really bad way to go. Somebody leaves their coffee out and the world's over in a few hours. Or it just cools down and gets closer and closer to room temperature. That's probably more accurate. Now, look at my curve. When is the steepest descent? When is it going to cool down the fastest? Think tangent lines. When is it going to cool down the fastest? Anybody? What do you think?
In the beginning.
The very beginning,
Right when it's right when it's fresh.
right when I set it down is when it's cooling down the fastest. You've heard things about cars, right? The moment you drive it off the lot, it depreciates the fastest. It's actually the exact same mathematics, believe it or not. This is called exponential decay. I'm not growing, I'm decaying. But it decreases really fast here, but over here, maybe it only changed 1/10 of a degree in the last 15 minutes. It's barely moving after all, you're right. So the rate of change is the difference between the temperature and the ambient temperature. That determines the rate, and this is the differential equation. Big T will be temperature, little t will be time. dt is equal to k times t minus a. A is a constant, that's the room temperature. Big T is how hot the cup of coffee is at any moment in time. It's big T of little t. This is the differential equation that governs this. Okay, so you with me so far? So if T is really far from A, then the rate of change is going to be big. But if T is really close to A, like here, the rate of change is going to be very small, but it's never going to be zero. So I would like to solve this differential equation. Okay, so let me erase this part here. Now what we're going to do is we're going to say 1 over capital T minus A dt equals K. And like before, we're going to integrate both sides with respect to time. So I have 1 over capital T minus A times this integrated with respect to T, but we saw before, that's equivalent to saying this. dt integrated with respect to T is the same as this. The right side, okay, hopefully, oh, you guys can't see that, can you? Okay, I'll write it underneath. I just looked up and I saw the glare picture. All right, so on the left side, it's 1 over T minus A. dt integrated with respect to T is big DT. The right side is K dt. That looks a lot like our population growth. And again, this is going to be a logarithm. So on the left side, I'm going to have the log of the absolute value of T minus A. On the right, I'm going to have KT plus, we'll call it C1, just like before. I'm going to exponentiate just like before. So I'll get capital T minus A equals e to the KT plus C1, which equals e to the KT times e to the C1. We'll call that C2. Boy, we have a lot of constants here, don't we? We have a lot of constants, but we actually know 2 of these constants. We know them right off the bat, okay? If we call T sub 0 the initial temp, this would be the temperature when I first placed the cup of coffee down. I have to know exactly what that temperature is, otherwise nothing afterwards really matters. I know exactly how hot this coffee is. At 140 degrees, it burned my tongue. That's T sub 0, okay? I know the ambient temperature. I know the room temperature, that's capital A. What I don't know is little k. We have to calculate that, but I know everything else. So right now, looking at my picture, I can say that T of T equals, now I'm going to add the A to the other side, A plus C2 e to the KT, okay? It appears that I have a lot of constants. Well, that's a given. That I can now figure out because at time 0, I'll use a different color here. At time 0, that's how hot my coffee was right when I set it down. So T of 0, which we'll call T0, that equals A plus C2 e to the 0. Oh, but that's 1. So that means that equals A plus C2. I know that temperature. I know that temperature. Therefore, C2 must equal T0 minus A. That's no longer an unknown. Awesome. We're almost there. So let me write down what we do know. So with this situation, we now have the temperature at any time is ambient plus T0 minus A, which is just a constant, e to the kt. I still have to calculate little k, but that's a constant that's known. That's a constant that's known. This process, this formula is called Newton's law of cooling. And that is Isaac Newton. Newton's law of cooling. This is an absolute with the one condition that the room temperature environment is constant, that there actually is a constant temperature. Newton's law of cooling will allow us to predict the temperature in the future, to predict the time it takes to reach any individual temperature in the future. It's cool, but the problem is I still have an unknown. So what has to happen is as follows. I know the ambient temperature. I know the temperature of my cup of coffee. Picture this. I have my cup of coffee in a well-insulated thermos with a cap on it. Is that coffee going to cool down very fast? What do you think? Is that going to cool down fast, or is that going to be really slow? It's in a well-insulated thermos with a cap on it.
Very slow.
Probably very slow. I'm going to pour my coffee into a cereal bowl, big open cereal bowl. It's really exposed to the air. Is that going to cool down slow or fast, do you think?
Fast.
Yeah, probably fast. So just because the coffee's hot, it doesn't guarantee how fast it's going to cool. So here's what has to happen. I have to take one temperature reading in the future. The future, let's say, might be 1 minute, might be 10 minutes, or so on. So let me show you what the picture looks like. So going back to my original picture, we were here, we agreed that it's going to do this. I know this, so I pick some arbitrary place in the future and I measure the temperature. I measure the temperature in the future. That means you give me a particular time and I will have a number here. I will have a number for t. I can then calculate the k. K will be a logarithm. Whenever you're solving for an exponent, your answer is a logarithm. Once I find the value of k, now there's no more unknowns. And I can then use this to predict and so on. I'm going to show you where this is considered one of the most practical of all differential equations because of its use, okay, and how many different ways this can actually be used. So let's, again, when I give you an individual time, you can predict that k. So let's do a simple example of Newton's law of cooling, shall we? Oh, and by the way, I kind of want you almost to start in the future. All right. So let's suppose that let's say we have something really hot. So let's say we have a 300-degree piece of metal. It is placed in a room of temperature, we'll keep it simple, a room of temperature, how about 75 degrees, okay? In 10 minutes, the metal, let's say, has cooled, is then, let's say it's cooled to 250 degrees. So we want to do two things, okay? We want to find T of t. That means we want to find a general equation that always describes this, and also find the temperature after, how about 20 minutes? So we're going to find T of t, and then we'll find T of 20. We have enough information. Here's why we have enough information. That's T0. That's A. That's T of 10. And that's my one reading that I needed. That's all I need. See, in 10 minutes, it might be hotter than this, it might be colder than this, but that determines everything else down the road. So for this problem here, we can start here, okay? So let me erase this. So for the problem that we're doing, we know that T of T equals 75, and we'll use degrees, it's easier. What's T0 minus A? Anybody?
225.
225 e to the kt. Great. That's the equation that we're going to start with. Okay, now what information do we know? We're only given one thing at this point, and that is that T of 10 is 250. Okay, now look at the right side. That's 75 plus 225 e to the 10k. I'm replacing t with 10. Everyone sees this? From this equation right here, that's the only unknown, so I can now solve for k. And when I solve for k, the rest of the problem will just fall into my lap. So let me erase this. I don't like erasing things as I go, but I need the space. So let's see, if I throw the 75 over, then I have 175 equals 225 e to the 10k. If I divide, then I have 175 over 225. And by the way, does that come out nice? Is that a nice number? I believe that's exactly 7/9. I don't want a decimal. Whatever you do, avoid decimals as you go. You're going to get round off error. 7/9 equals e to the 10k. So finally, if 7/9 equals e to the 10k, that means that 10k equals the natural log of 7/9. And finally, k equals 1/10 the natural log of 7/9. Oi. And Mr. Brown says, don't convert that to a decimal. No, don't convert that to a decimal. You might need a calculator in this problem, but you won't need it till the very last step if you do it right. And here's why. Tell me, this is algebra. If I said to you e to the log of thing, what does that equal?
Thing.
Thing. You're going to take a logarithm and you're going to put it up into the exponent. You're going to have an e to the log. Why would you want to calculate the exponent and then go e to the decimal approximation to get a different? No, too much rounding. You don't need to do that. When you do e to the log and all that, you're going to get a rational number. You're not going to get a decimal. Now, you might not get a happy fraction, but you're going to get a fraction, not a decimal approximation of a fraction. And that's kind of beautiful. So how do we do that? Well, we're going to take that k. Now, I just want to look at this statement right here. So I have e to the 1/10 log 7/9 times t. Yikes. But wait a minute. We know a rule of logarithms. Isn't log x to the a the same as a log x? Those in my class, you know what sound it makes, right? You can always do that, which means you can always back and forth. Can you think of this as e to the log 7/9 times, all right, let me put this one. Let me put the t over here. Let me write it that way. T over 10 log 7/9. Okay, you with me? Can I move that up to the exponent? Yes? No? Maybe? This is not calculus, this is just logarithms. I have t over 10 log 7/9. That's the same as log 7/9 raised to the t over 10. I have e to the log of thing. So e to the kt is equal to this. Ooh, that's way better. E to the KT is exactly equal to this quantity here. I like that. I have no decimal approximations and I can give an exact value and I might not even need a calculator to do this problem. Beautiful. So let's go back to here. And now that means our function is 75 plus 225 times 7/9 to the t over 10. This is our function for any time t. So if you ask the question, well, when will it cool down to 100 degrees? When will it cool down to 200 degrees? Then I would set this equal to that value and I solve for t. I'm asking what's going to happen in 20 minutes. So in 20 minutes, let me erase this. T of 20, I'm going to replace t with 20, is 75 plus 225 times 7/9 to what power, folks? What power? If I replace t with 20, I have 20 over 10. That's just second power. Okay, now let's calculate this. Now I can use my calculator. All right. And does everybody have an answer? I got an answer. Tell me when you get a number, anybody. Just holler it out.
Oh, 211.
Yeah, it's, in fact, it's 211 and a ninth if you want, right? Because it's 0.111. Or if you wanted to say, this might be a cleaner answer, 0.1. Now, does this answer make sense? This is huge. Okay, there are some bad answers. I have a 300-degree object and I'm putting it in a room that's much cooler. In 20 minutes, that object better not be warmer than 300. Agreed? It getting warmer is probably bad. Okay, it cooled down 50 degrees in the first 10 minutes. In the next 10 minutes, it can't cool down 50 or more because I'm closer to room temperature. It has to cool down less. Every 10 minutes, it's got to be less. In the first 10 minutes, we cooled down exactly 50 degrees. Now we cool down a little less than 39 degrees. That makes sense. It's slowing down. So that answer makes sense based on our information. So if I ask the question, well, how long do I have to wait till it reaches a certain temperature? Then you you set this equal to that number. Newton's law of cooling turns out to be one of the more practical tools we actually use in everyday real life. And I'm going to give you some examples. Okay. Does Newton's law of cooling work? There was a hiker. They were out hiking and we didn't see them for several days. And then an accident may have occurred and we find them. My wife actually knew somebody, this is awful, many years ago, somebody she worked with, they didn't show up for work. They got mauled by a mountain lion while they were hiking and they didn't find them for several days. Will Newton's law of cooling work to determine time of death for that person? Hiker. What do you think? Somebody who's hiking and they disappeared and we're trying to determine how long ago they died. Why can't we use Newton's law of cooling?
Temperature is changing.
It's variable.
Because they're outside, yeah, temperature is variable. So when you were going hiking and then a avalanche and you were buried in the snow and frozen and they found you 1,000 years later, you were still like that. Why won't Newton's law of cooling work on that one? I was in a constant temperature environment. Yeah, you were frozen solid. Yeah, no, that one won't work. No, it has to be a constant temperature environment and the time interval cannot be too long. The reason is when that coffee cooled down and now it's almost room temperature, an hour or two later, it's not going to change hardly at all. And my ability to measure is not very good over a long period of time. I'm talking about, thousandths of a degree. Where Newton's law of cooling is actually used, believe it or not, is time of death. If it's a short duration. Now, strangely enough, this is just weird. I live in a really nice little residential area. And I've lived in my house for just about 20 years, and we have had 3 different neighbors die. Old, very, very, very old neighbors die. And the weird thing is this happened on both sides of one particular house. And one of our neighbors has had the misfortune of discovering them because he would help them out and bring them meals and stuff. And there were like 90 somethings. They died in their homes, all sealed up, constant temperature. They actually are able to work backwards to figure out time of death, more or less. If we make one simple assumption, if we assume before they died, they had a semi-normal body temperature. And what I mean is, around 98 degrees. And maybe they just died, old age. And as long as they don't wait too long, they found them within a day, usually each time, and they can work backwards. You say, how can you work backwards? Again, you have the ambient temperature, okay? We're assuming this. What we're doing is saying when they found them, they were here, and they say let's say is the time, this is when they died. That's their body temperature. 98, 98 and a half, somewhere there. We find them when they die, what is their core body temperature? And then maybe a short distance of time later, find their body temperature again. You can work backwards and say, how long ago was that temperature this? I know it sounds morbid, but that's actually how it's done. If it's a short period of time, constant temperature environment, and they assume a relatively normal body temperature, okay? That's not the big one though. Does anybody know what the most powerful companies in the country are, technically on planet Earth? But let's just leave it to the United States. What are the most powerful companies? Anybody know? It's not even close. What happens to you if you die? Hopefully you have life insurance and your next of kin or whoever else is going to get a really large sum of money. If every single person in the United States died right now, life insurance companies could pay off everybody. Life insurance companies are the most powerful entities on earth. So what do you mean? Life insurance companies are worth more than entire countries, like several fold. All the wealth on planet Earth doesn't add up to what life insurance companies are worth. If the life insurance companies could pay $1 million for every person in America if they died tomorrow, that's not measured in trillions, that's measured in quadrillions. Life insurance in general are the most powerful entities. And you know this because insurance companies they operate outside of the law. I don't mean they can perform illegal activities. I mean, insurance cannot be taxed. If you're left a life insurance settlement, or you get an auto insurance settlement because of an accident or any time, that cannot be taxed. Insurance cannot be touched by any government. So the reason I'm pointing that out is insurance companies, being very powerful and very wealthy, they want to get it right. And I'm not saying they're not doing anything illegal. No. Your insurance rates, it's all mathematical. It's based on what's called actuarial science. I studied that a long time ago. It's based on the probability of and likelihood of you getting in an accident or you dying based on your lifestyles and things like that. That's how your rates are determined, based on the likelihood of something happening. But insurance companies don't like to pay out if they don't have to. So my brother, who runs an insurance restoration company, it's a very big company in San Diego, he's who comes to your rescue if you have a fire in your house or you have a flood. They come in, they fix everything and make it right. Sometimes he deals with big buildings in San Diego that may have burned down. So I'm going to use that one because homeowners insurance is extremely expensive. Anybody here who's a homeowner understands this. You can get away with a lot of things, but one thing you can't do in the United States, you cannot own a home and not have homeowners insurance. If you have a mortgage, you're absolutely required by the mortgage holder to have insurance in case something goes wrong. So insurance companies, particularly homeowners insurance, are really careful about paying claims. Now, my brother will go investigate a fire. There's only 2 ways a fire can occur, and they both begin with A. Anybody want to try? I'm talking $1 trillion industry here.
Arson and accident.
Arson and accident. And it's up to the insurance company to figure out which it is. So they send in their specialists. You got a giant building, it's been gutted, it's been burned down. And using differential equations, now not what we're doing, we're talking very high level differential equations. I'm just giving you a brief picture. Using high level differential equations, you can actually work and find the exact place in space. You can work backwards. They're called heat signature trails. you can work backwards using differential equations to find the exact place in that huge building where the fire started. So you see it next to a grate and you see some old faulty wires that may be caught and you go, okay, yeah, bad wiring, accident. But this is one of the craziest ones. My brother was telling me about this a couple times. They found almost microscopic traces of the gas-soaked rag that started the fire. Clearly arson. And at that point, people are going to jail because, that's fraud. Yeah, you can get away with a lot of things, but insurance fraud ain't one of them. But it's incredible mathematics and science that you can actually pinpoint the start of the fire where it occurred. So it's a version of this. It's a version of this on steroids, but it's a version of this. Newton's law of cooling is such a powerful entity. Now, in a more practical note, okay, have fun with this. I won't mention the name, but a certain restaurant back in the 90s and early 2000s was notorious for serving their coffee at their drive-through at 140 degrees. Now, if you ever have coffee, 140 degrees is way too hot. 120 might be more palatable. You'll burn your tongue. But if you serve coffee really hot, it stays hot longer. Serving ridiculously hot coffee in a styrofoam cup, and the people would go through the drive-through and then of course do the smartest thing known to man, and that is put the hot coffee between their legs while they're getting ready to drive away. Then having it spill, cause literally third-degree burns, and then turn around and sue the Mc company again, which I won't mention. And so the Mc company, after having paid hundreds of millions of dollars of lawsuits because of burn victims, because they served their coffee too hot, finally figured out, maybe we should wait a little longer to serve that coffee. So what they did was they figured out exactly how many minutes, it's actually this, do I let the coffee sit before it reaches a particular temperature, then it's a safe temperature to send out. And voila, no more lawsuits. I mean, to me, that was kind of common sense. You serve something that hot. I was always amazed the fact the majority of the burn victims, it was their legs because they had the coffee between their legs. Why you would put hot coffee between your legs while you're driving, to me, is beyond reckoning. And some of you might be laughing because maybe that's what you do. No, that's what cup holders are for. I have a friend I won't mention, and his wife was a PhD professor at San Diego State and did that to herself. And she was too embarrassed to sue because she said, I'm way too smart to have done this, but she had third-degree burns in her life. Yeah, kind of a crazy one. But Newton's law of cooling, really cool subject. And if you notice the mathematics involved, exponential and logarithm, can't really get away from those guys. They're there, very, very powerful. Okay. Now, I'm going to take you to the next level of solving a generic general differential equation. But before I do, let me open up really quickly. Let me go back to gallery for a moment. Does anybody have a question on what we just did? Because we've solved population growth. This is a version of population growth. And by the way, there's another version of this I point out. If I take the frozen chicken and I put it on the kitchen counter in the constant temperature environment, everybody understands what's going to happen, right? Chicken will what? It'll start thawing. And eventually it will reach room temperature. The problem is it'll keep going. It'll get hotter, 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 eventually burst into flames, potentially become supernova, burning up all of the oxygen in the atmosphere, and then we're basically just a wasteland. Or it's also asymptotic the other way. See, Newton's law of cooling also applies to when something's heating up. So hopefully we don't turn into a ball of fire or a frozen wasteland, that we're approaching room temperature. We never actually reach room temperature. So let me give you the generic on solving a differential equation, and then we're going to look at one really, really cool application of that, because today is all about differential equations. None of the calculus so far, hopefully, has been taxing. So I want to solve the following problem. Let's say this equals, I want to keep this simple. Let's say x squared over e to the y. I want to solve the following differential equation. Now, dy dx, that statement tells me y is a function of x. I'm differentiating with respect to x. So if it is possible, I would like to write my final answer as y equals, if it's possible. It may be difficult, in which case I just anything I can come up with is almost fair game. So how do I solve this? This is what is called a separable differential equation, just a separable DE. And so what I want to do is I want to get the y on the other side. So I'm going to have e to the y dy dx equals x squared. Now when I integrate both sides with respect to x, the left side is going to be e to the y dy dx integrated with respect to x. I'm going to go ahead and just say dy. And the right side is x squared dx. dy dx integrated with respect to y is dy. Now I want you to notice something. I could literally have just gone from here to here. This is what is called a separable differential equation because I can separate the function of x and the function of y. If the function of x and function of y are connected as a product or a quotient, then I have a separable differential equation. If x and y are being added or some other combination, I can't pull them apart. But because these were in a quotient form, I could pull them apart. Now the problem comes down to just solving this, and that's not that hard. So the left side is e to the y. The right side would be 1/3 x cubed. I only need to put the plus c once, so I'll put it on the right side. And I said, if possible, we want to write y equals. So y equals natural log of 1/3 x cubed plus c. So the solution to this separable differential equation is this function right here. If I gave you an initial condition, that would allow you to solve for the c. If I don't give you an initial condition, then that's the answer, and you just walk away. You're okay with that, right? Nothing wrong with that. So let me now throw in an initial condition just to show you what it would look like. So an initial condition might be something like this. How about y of 0 equals 3? That will be my initial condition. Y of 0 equals 3. So that means if I replace x with 0, y is 3. How do I get to that? Well, I can do it over here. Okay. So if I wrote e to the 3rd power equals 1/3 times 0 plus c, that would mean that c equals e to the 3rd power. And that would go right here. Okay, that's an example of how that would work. You don't change anything if you have an initial condition. You just do the one additional step to find the c. Right, so let's try another one of these. And this is called separable because I can pull it apart. Now, the way a separable often is presented is actually a little bit different. The notation we use often looks slightly different than this. I might write it this way. Secant y dx plus, how about if I write x dy equals 0. Now this is a little different. I didn't write it in dy dx form. I've already got it sort of pulled apart. So in this case, remember, dx and dy are instructions. They tell me what I'm supposed to do to integrate. Oh, can I just integrate both of these? Well, not exactly. The variables don't match. Oh, so I've got to do a little bit of algebra. I would like it to look like this did, but it's not going to look like that quite yet. So there's a step I need to do first. I need to get x with dx and I need to get y with dy. So the first thing I'm going to do is put these on opposite sides. Now I'm going to multiply both sides by the reciprocal of secant and by the reciprocal of x. Okay, if I multiply both sides by the reciprocal of the x, then I'm going to have 1 over x dx. And the reciprocal of secant, of course, is cosine. So on the right side, I'm going to have negative cos y dy. So again, I multiplied both sides by the reciprocal of secant and both sides by reciprocal of x. Aha, now I have something that's not going to be difficult at all to integrate. So now I'm going to do that. So the left side is natural log absolute value of x. The right side, negative sine y plus c. If I was given an initial condition, I'd solve for c. If not, I just leave it alone. Now, I would really like to write y equals if I can, but if I can't, that's okay. So let me show you an alternate form of an answer. In a lot of textbooks, you might see the following. Because of the way I asked the question, by having a dx and a dy, I did not make it entirely clear that x was independent and y was dependent. It could have been dx dy. Y could actually be the independent variable here. So when I write it this way, it gives me the freedom of writing my final answer as x equals, y equals, or neither. What if I added this to both sides? And I'd have log x plus sine y equals c. This is also considered an acceptable form of an answer. Now, the only reason you do this is maybe it's difficult to solve for one or the other. Solving for y wouldn't be hard. I get the sine by itself, I throw the log over, I'd take inverse sine, piece of cake. Here, I go e to both sides, I've got x. That's not really the issue. I'm just showing you there's an alternate form. What it comes down to is, what am I going to use this answer for? Now, a lot of you are taking physics right now and you understand, let's say we have a really big physics problem. You haven't had any yet, we're only week 2. But in a really big physics problem, maybe you have to do some calculus during the problem. So you perform your calculus. Whatever you get is not the end of the problem. You're now going to use that answer to go further in the problem. Whatever answer you get to the calculus question in real life, it's rarely the end of the problem. I'm done with the calculus, but maybe I now need to use this further in the problem to answer more stuff. So when people say, what form should I write this in? Should I write it as y equals? Should I write it as x equals? Should I put them together? The answer is yes. You do whichever one is the easiest to work with within the problem you're looking at. So if I have to do stuff later involving, x's, maybe writing y as a function of x might make my life easier. If there's a statement that looks like this later, maybe it's going to cancel. Maybe this is the best form. The best form is whatever is the most useful within the problem. There's no one answer to that question. Okay, you just do whatever's there. Solving a differential equation means I'm going to integrate both sides, okay, with respect to x and with respect to y. And then whatever I get, if I can solve for one of the variables, that's usually considered a preferred version of the final answer. So now we're going to go to a really cool application of this. Okay. Now there's a math word that a lot of you are not very familiar with. In Calc 3, they use it all the time. And the word is orthogonal. Anybody who's heard of this word, what's another word that sometimes means the same thing? Does anybody know?
Is it isometric?
No, it's a geometry kind of thing.
Parallel. Perpendicular.
Good. If you're perpendicular, then you are orthogonal. Orthogonal is a little bit bigger. It's a little more wide reaching, but you got the right idea. Lines and planes. We see perpendicular, right? Perpendicular lines. Anything that meets at a right angle. Look around your room. I've got a wall, I've got the floor. Those are perpendicular planes. I'm standing with good posture. I am perpendicular to the floor. All of those are correct statements. Orthogonal, I am not limited to lines and planes. Perpendicular, you have to be straight because you can't measure an angle between things that are curvy. So I want to introduce a couple of simple concepts to make this bigger picture cool. Parallel. Let's start with parallel because that's an easy one. And most people, believe it or not, have an incorrect version of parallel because when we think parallel, most of us do the same thing. We think baby algebra. When I think parallel, I think two lines on the XY plane. Those are parallel. And that is a really good example of parallel. Problem is we live in 3D. And so we kind of need a bigger version. So parallel has exactly 3 aspects. Parallel means, first and probably most important, is non-intersecting. equidistant, same direction. If I get any two of those three, I'm parallel. Now, non-intersecting. You say, well, isn't that enough? All right, here's what I want you to think about. Look at your ceiling. Just imagine there's a line on your ceiling. In any direction, you took a felt pen and you just made a line on your ceiling. Now look at your floor, just draw a line on your floor. Right, you can have think of something like that. Can those lines ever intersect? Anybody? Take any line you want on your ceiling, take any line you want on your floor. Can those lines intersect?
No.
No, because the planes they are on are parallel. But those lines are not parallel. Their lines are called skew. Two lines in space that do not intersect are called skew. They're probably not parallel. And the example I like to use is think of flight patterns. Flight patterns leaving an airport. Would you say that flight patterns must be non-intersecting? That's not a joke. Would you say flight patterns must be non-intersecting paths? Because if they're not non-intersecting paths, we could have mid-air collisions. So all flight patterns are on non-intersecting paths, but no flight patterns are parallel. Otherwise, we'd all be going to the same place. Oh, so parallel non-intersecting is important, but if I'm in 3D, non-intersecting does not mean parallel at all. Same direction. Oh, so if I'm non-intersecting, but I'm in the same direction. Now think railroad tracks. Railroad tracks are not necessarily straight, are they? But one thing is true, they remain the same distance apart. They're equidistant. Because if the railroad tracks weren't equidistant, if they got wider or got more narrower, the train would come off the track. That would be bad. If anybody's getting in their car today and going on the freeway, are you going to have an example of parallel while you're on the freeway? Think about that. Will there be any examples of parallel while you're on the freeway?
Yes.
You get in your lane, and what are you doing? You're going like this. Oh, by the way, are your lanes perfectly straight on the freeway? No, they curve. But what can you say? Your lanes are equidistant. They don't get narrower and wider. The dotted lines go in the same direction at all times, and none of your lanes intersect. That would be bad, by the way, if your lanes actually just randomly intersected. The lanes on the freeway are a perfect example of parallel. Not parallel lines, just parallel curves. Oh, surfaces can be parallel. Parallel means those things I said, equidistant, non-intersecting, same direction. Now, if they happen to be lines, that's great, but they don't have to be lines. Now, orthogonal, much like parallel, orthogonal has way more going on. Now, orthogonal, there is something going on with right angles. I have two curves. Clearly, those are not straight, so they cannot be perpendicular because no angle can be measured. But consider the tangent line to this one and the tangent line to this one. Could those tangent lines be perpendicular? Would that be possible, that the tangent lines are perpendicular? Anyone? Yes, no, maybe?
Yes.
The tangent lines could be perpendicular. Then we'd say the curves are orthogonal. Now, I want you to think of a sphere. Think of a basketball. Okay, we all know what a basketball looks like. You can't make an angle with any part of a basketball. It's curved. Yeah, I can draw spheres. All right. So let's consider, I'm going from the center of the basketball straight out through the top of the basketball. Kind of like, you put the thing in to do the air. Imagine there's something at the center of the basketball and it goes right through the basketball and it keeps going. If I took a piece of cardboard and I touched a basketball at any point, technically that piece of cardboard should only touch the ball at one point. I'm not squishing it. That thing would be called a tangent plane. So imagine the piece of cardboard, you're going to touch the basketball, and now you got that line going through the basketball. That line going through the basketball is going to be perpendicular to that tangent plane. Therefore, that line leaving the basketball is orthogonal to the basketball because it's perpendicular to the tangent plane, just like my last example with tangent lines. So orthogonal curves are curves whose tangent lines are actually perpendicular. Orthogonal surfaces are surfaces whose tangent planes are perpendicular. We're going to limit it to that. Okay, so that's what it means to be orthogonal. I now want to ask a simple question about what if I wanted curves that were orthogonal to other curves in general? Now, consider the following, okay? I have a family of circles, okay, infinitely many circles. I can draw circles, I can't draw line segments. I would like to know, is there a set of curves out there or of functions, doesn't matter what it is there a set of things out there that's orthogonal to every one of these circles at the same time? Whoa. You know, I could make parabolas and ask the question. I could do exponential functions and ask the question. I could do anything and ask the question. So what we want to do is figure out how do I do this? Well, we agree that these are circles centered at the origin. So they probably have this equation. I would like to know a set of curves that are orthogonal to this set of curves. Now I said when it's curves, we're talking about tangent lines. How do you get a tangent line from any function? What do you have to do to come up with a tangent line for any function? What do you have to start with? Tangent line. Tangent line. How do you find tangent lines to any function? We know the answer to this.
Derive.
So I've got some function and I want something, I want that tangent line. What do I have to do?
Find the derivative.
I have to find the derivative. Good. I have to find the derivative, and the derivative evaluated at that point is the slope of that tangent line. Okay, so in order to find tangent lines, I have to take derivatives. No way around it. All right, so what I want to do is find dy dx. Now we did that in Calc 1. We found dy dx. The easiest way to find dy dx is to differentiate implicitly. In fact, that's pretty much what I have to do. So if I differentiate both sides of this with respect to x, then what will I get? I'll get 2x plus 2y times dy dx equals, the radius is a constant, so it would equal 0, would it not? Now I need to solve for dy dx. I'll put it up here. So 2y dy dx is going to equal negative 2x when I throw that over. So dy dx is going to equal negative 2x over 2y, or just negative x over y. Now in Calc 1, we actually do this problem. We realize that the slope of the tangent line at every point on the circle centered at the origin is going to be just negative x over y. See up here, x is 0, so the slope of the tangent line is 0. Right here, the y is 0, so the slope is undefined. Oh, okay, that makes sense. Okay, anywhere in the first quadrant, I should have negative slopes. Anywhere in the second quadrant, I should have positive slopes because now my x's are negative. Okay, great. I just told you what the slope of the tangent line is at every point on the circle. But I would like the set of curves that are orthogonal to these. Now think about baby algebra for a moment. Think baby algebra. If I said I had a line, I have a line, and the slope of my line, let's just say, was 1/2. Tell me about a line that's perpendicular to this line. What would its slope have to be?
Reciprocal?
Well, then that would be this way. You're half right.
It's the opposite reciprocal.
Yeah, the opposite sign reciprocal. So if the second line had slope -2, do you agree that that line would be orthogonal or perpendicular? You remember this from baby algebra. Basically, the rule is if the product of the slopes is -1. So it's not just the reciprocal, it's the reciprocal with the opposite sign. That's how you were able to work with perpendiculars in baby algebra. So if I said, Mo, one of my lines has slope 2/3, the other's got to have slope -3/2. One of my slopes is -5, the other's got to be positive 1/5, and so on and so on and so on. I have a curve, and every point has that slope. I would like the set of curves that are orthogonal to this. So what slope should I use? I'll use a different color. Anybody want to try that one? What
Would it be
slope
y
should
over
I
x?
use? Say again?
Y over x.
Positive y over x, exactly. That's the slope I should use. The set of curves where this is true will be orthogonal to this set of curves. Absolutely guaranteed, because we just figured out how to make our tangent lines perpendicular. So now I need to solve this differential equation. Sound familiar? That's what we just got done doing. That's a separable differential equation. I can actually pull it apart, and I could write this as 1 over y dy equals 1 over x dx. Stare at that for a moment. I multiply both sides by 1 over y and want to integrate with respect to x. The dy is alone. Boom. So let's continue. I have no idea what the answer is going to be yet. So the left side is natural log absolute value of y. The right side is natural log of x, and then I have to have the plus c. That plus c actually is quite important. Boy, I don't want to exponentiate both sides because I don't know what I'm going to do with that c if I do. At least not yet. What if I did this? Log y minus log x equals c. We have a log property here. Do you know what the log property is? The difference of logs is what? Anybody?
The division of logs.
Exactly. And this will make it much easier on us. Okay. I'm going to go ahead and I'm going to erase this up here because we've got this. The difference of the logs is the log of the quotient. Can I now exponentiate both sides? Yeah. The absolute value of y over x equals e to the c, let's call this c1, how about? Which is just some other arbitrary constant. Now, absolute value cannot be negative. Do you agree? Absolute value cannot be negative. But can the individual x's and y's be negative within the absolute value? Is there anything wrong with that? What do you think? Can either the x or the y be negative inside the absolute value? Sure, because then when I take the absolute value, it makes it positive. Oh, but I want to remove the absolute value. Now I'm going to remind you of something you already know. If I said, just think baby algebra again. If I said the absolute value of x equals 3, doesn't that mean that x is plus or minus 3? Isn't that something we learned in algebra? If the absolute value is 3, then x could be 3 or negative 3. That's okay. So I want to remove the absolute value. So if I do that, I get y over x then is plus or minus c2. So y is plus or minus c2x, because c2 was any positive number. So that means y is any number, positive or negative, times x. Wait a minute. Y is any number times x. Y is any number times x. Isn't that just a line? In fact, it's not just a line, it's a line that passes through what? Y equal x, y equal 2x, y equal a half x, y equal 10x, y equal a third x. It's a line that
Origin.
passes through
The origin.
what? The origin. Huh. So are you telling me that do you see it? Is it obvious? Oh my gosh. My set of orthogonal curves will be lines through the origin, and it's pretty easy to see that these lines will all be orthogonal to these circles. That's crazy, but that's what we just proved. This, now I'm going to give this a name. What we just did is called finding the orthogonal trajectories. A trajectory, think of it like I'm leaving and going in a particular direction, an orthogonal trajectory. I found a family of curves that was orthogonal to every one of these circles at every point of intersection. There's infinitely many circles, there's infinitely many lines, and every one of them are orthogonal. I mean, that's just crazy, but it's really cool. We could do this with anything. Now, orthogonal meant that all the tangent lines would be perpendicular. It's a family of curves, so there's infinitely many. This is a very useful one. Now, I love using movies to illustrate points. And those of you who've been in my Calc 1 class, we proved the fundamental theorem of calculus, as you know, by using the original Star Wars, the garbage, they're in the garbage pit. Remember, the walls are closing in. That's how I actually use that to prove the fundamental theorem of calculus, is delta x is approaching 0 and all that stuff. Well, turns out if you're a Star Wars fan, Darth Vader is really big on differential equations. There's so much calculus in life that you're not even aware of. When we get to Calc 3, you know, the cat in the hat, oh yeah, that explains three-dimensional functions because he has thing 1 and thing 2, which are two independent variables, and that's how we describe everything. Well, in the second Star Wars movie, okay, I'm not gonna, there's no spoiler alerts. It did come out in like 1980. So if you haven't seen it yet, you know, there's a scene where Darth Vader's in his little dome and he's doing whatever they're doing, you know, giving him oxygen, whatever. And the Han Solo and his guys, and they were, you know, sneaky, stuck to the ship, and they eventually floated away. You remember? And then Boba Fett chases them and all that stuff. Well, the guy comes up to Darth Vader and says, you know, we lost them. They went through an asteroid field, and of course, Darth Vader says something to the effect, you know, asteroid fields do not concern me, Commander. And then he says, plot a course. Does anybody remember the exact words? On their last known what? Trajectory. He's actually using perfect mathematical description. He's also giving you exactly the mathematics behind what are called search and rescues, like out in the ocean, when they're trying to find a ship that's been lost at sea. You're using trajectories, directions of travel that you can then predict where something's going to be in the future. So like I said, Darth Vader was a big Diffie-Q guy. He didn't really love calculus all that much, but he liked the Diffie-Qs for the applications part, I think. At least that's what I believe. So a trajectory, again, it's going in a particular direction. Typically, the concept of a trajectory is you're traveling straight. Okay, so when I say last known trajectory, that would be in a tangent direction to whichever way we were going. And again, that's really important in real life when we're trying to find things. So we talked about population growth. We extended that to Newton's law of cooling. Then we extended that in general to solving separable differential equations. And then we extended that to being able to solve orthogonal trajectories, which are a very particular type. These ones are really, really cool. But the amount of calculus you're performing, you're going to integrate maybe a polynomial, a sine, a cosine, an e to the x. The integration itself, trivial. That's not something you should labor over. But again, if you're rusty, you got to go back and practice some of the stuff. That's all. All right, I'm going to stop recording now.